So hi everyone, welcome to Talk Math with Your Friends, a special episode with My Favorite Theorem. Because we're also recording this for a podcast, we've left everyone on mute. You are still welcome and encouraged to use the chat. After they have a conversation with Annalisa Cornell, we're going to have a Q&A. And so there'll be an opportunity to either unmute individuals to ask their questions or I will be monitoring the chat and amplifying the questions. So if you particularly want it to be asked to our guests, please maybe indicate that maybe with a star at the start of your question, but you're welcome to talk with each other. And then, assuming there's time, which I think there will be, we're planning to have some flash favorite theorems as part of it. That'll be much more audience participation. So please join me in welcoming Evelyn Lamb, Kevin Knudson, and Annalisa Crannell to Talk Math with Your Friends.
Yay. Well, if this were actually the podcast, this is where you'd hear our intro music. So I'll do my little impression. Do 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 do. Okay, welcome to My Favorite Theorem. Joining forces today with Talk Math with Your Friends. I'm Evelyn Lamb. I co-host this podcast. I'm a freelance math and science writer in Salt Lake City, Utah. And this is your other host.
Hi, I'm Kevin Knudson, professor of mathematics at the University of Florida, where it is boiling hot today, and I'm very happy to be in this, how would they put this on TV? A crossover event, right?
Yeah.
Right, so like I think last night on NBC on Wednesday nights, there's like all these shows that take place in Chicago, right? There's Chicago Med and Chicago PD and Chicago Fire, Chicago Uber, who knows what. Anyway, and sometimes they'll just merge them all into one 3-hour super show, right? So here we go. This is the math version of this, right?
Yes. And I realized today that our very first episode of My Favorite Theorem, we published that in late July 2017.
That's
so
correct.
This is our early third birthday, and we're so glad that people came to join us. And we are very happy today to have our guest, Annalisa Cornell, with us. Hi, Annalisa. Can you introduce yourself and tell us a little bit about yourself?
So hi, my name is Annalisa Cornell. I profess mathematics at Franklin and Marshall College, which is in southeastern Pennsylvania. It's a small liberal arts college. I got my PhD working in differential equations, partial differential equations, nonlinear differential equations, switched into discrete dynamical systems, topological dynamical systems, but for the past 10 or 15 years have been really thinking hard about projective geometry applied to perspective art.
That's quite the odyssey.
Yeah, I was really influenced by Paul Halmos saying that one of the marks of a really good mathematician is that they can change fields. And so, yeah, I feel like I'm trying to enjoy so many different aspects of what this profession allows us to do.
And a fun story, at least it was fun for me, is that one time you were here in Utah giving a talk at BYU, which is down the street, and we went to an art gallery and you pulled out your chopsticks and showed me how you use your chopsticks to help you know where to stand to best appreciate art. And it was just so amazing to me that was this thing that you could do. So that was a lot of fun, and I think, I don't know, it just to me sums up the Annalisa experience.
Thank you. Yeah, summing, I guess, is a good thing for mathematicians. I think everybody should carry chopsticks with them. I mean, it's frugal, it helps you avoid trash, but it also helps you do really cool mathematics. So what's not to love about them?
Yeah. So what is your favorite theorem?
So if you had asked me about 5 years ago, I would have said the intermediate value theorem, but today I am going to say no, Desargues theorem. So Desargues theorem first came into human knowledge in the 1640s, and it's it's a theorem that sounds like it's sort of about planar geometry, but I really think of it as being about perspective. So is this what I'm supposed to tell you what the theorem says?
Yes, please.
Yeah.
Okay.
And should we all get out our, so this is one, I feel like I always need like a piece of paper with, oh, I'm trying to hold it up, but I got a Zoom background.
Yeah.
But I got my piece of paper out so I can hopefully follow along
So
at home.
if you had a piece of paper or a chalkboard right behind you, you could imagine that you would have a triangle like standing up on a glass pane, and then on one side of this glass pane would be maybe a magician or somebody holding a light. Maybe your granddaughter drew the magician. Okay, for people in the podcast, I'm showing a picture that my granddaughter drew on the chalkboard. This light shines on the triangle, then it casts a shadow, and the shadow is also a triangle. And so we say those two triangles are perspective from a point. The point is the light source. And we say that because the individual corners, the corresponding corners are collinear with the light source. So A and the shadow of A are collinear with a light. B and the shadow of B are collinear with a light. But it turns out that those shadows, the triangle and its shadow, are also perspective from a line. And what that means is that if you think not about the points on the triangles, but the three lines on the triangles, and you really think of them as lines, not line segments, so like going on forever, then the corresponding lines will also intersect along a line. And you can think of that second line, which we call the axis, is like the intersection between the plane of glass that's sitting up in the air and the ground. So the interesting thing to me about Desargues' theorem is that it pretends like it's a theorem about planar geometry, because this theorem holds when the two triangles are both in the same plane, in R2 or something. But the best ways of proving it, the most standard ways of proving it, are using essentially perspective, going out into 3 dimensions and proving it for 2 completely different planes, and then pushing them back down into the regular plane. And so to me, this is a really interesting example of sort of how art informs math rather than the other way around, or maybe that they both inform each other.
So going back a little bit, to me, when I've looked at Desargues' theorem before, somehow there's this big conceptual leap to me between perspective from a point and perspective from a line. Perspective from a point, like, it seems really easy to think about, and perspective from a line, I just have trouble getting it into my brain.
Yeah, I do think perspective from a point is so much more intuitive. And so the minorly intuitive, the somewhat intuitive way of thinking of this axis is you could sort of pretend like it's a hinge. So if these two triangles will sort of fold onto each other from the hinge, the triangle on the glass and the triangle on the ground can fold along this hinge, then they're perspective from a line. So if you think about something that's in the real world, a flat thing in the real world, and its mirror image, then those two, it's hard to say whether they're perspective from a point, but the lines in the real world thing and the lines in the mirror will intersect along the line where the mirror hits the ground. And so that's another way of thinking of this axis, sort of 3-dimensionally.
So I want to think about this in projective space, which probably isn't correct, or maybe it is. I don't know. I mean, so these lines are points in projective space. Is this how one might go at this in some other? Uh-oh.
Yeah.
I asked the wrong question. I'm sorry.
So I'm that's not exactly the way that I think of it, because I think of the line as a line in projective space.
Okay.
Yeah. And the point is a point in projective space. So the point comes from, you could say, from a one-dimensional line in
right.
our whatever. Yeah.
Mm-hmm. Okay.
Sorry, and so here's one of the interesting things about this theorem and about me loving this theorem. In 2011, one of my co-authors and I wrote a book on the mathematics of perspective art, and we used Euclidean geometry all the way through. We were giving a Math Fest mini course on this, and a young mathematician came up to us and said, I just love how you use projective geometry in art, because I learned projective geometry and felt like it had to have something to do with art, and you guys are the ones that explained to me how it does. And Mark and I turned to each other and were like, what kind of geometry? So neither of us had ever taken a projective geometry class. Neither of us had ever learned any projective geometry. We did not know that it existed. And so this young mathematician ended up changing our lives. We ended up working with her and really learning a bunch of projective geometry in order to come out with our most recent book, which came out last December. And so when you ask questions that get into like really deep projective geometry, I'm like, ooh, I have to write that one down because that's something else I have to go learn. So for those of you young mathematicians out there, I just want to say, like, learning new stuff and not knowing stuff is really so much fun. Don't be afraid of starting something new, even if you don't know it all.
And how did you first encounter Desargues' theorem?
Oh, man. So I first encountered Desargues' theorem when Fumiko Futamura, this young mathematician, had convinced me I needed to learn it. So I bribed an undergraduate to go through Coxeter's projective geometry with me because it seemed like that was the standard book. And Coxeter is like the famous guy in this realm, and he is completely non-intuitive. So I found Desargues' theorem in there, and I'm like, I have no idea what this means. The notation is awful, the diagrams are awful, everything about this is awful. And so I read through his book trying to say, what does this have to do with art? And that was a really fun way to read it. So we just decided Desargues' theorem is about shadows. So.
Okay, very cool. Wait, I had a question and now it's gone. It's a bad time of day for me. Maybe Evelyn has one.
Well, I was wondering, so I remember you have also given a talk about squares that kind of blew my mind, where I guess the thesis of the talk is that all configurations of 4 points are a square if you look at it from the right way. Is Desargues' theorem related to that theorem? I feel like when you said the word shadow, that is what like reminded me of that other talk.
Yeah, thank you. So that's really cool. So there's so most of us know what the fundamental theorem of calculus says. Most of us know what the fundamental theorem of algebra says. The fundamental theorem of projective geometry, in one sense, really ought to be Desargues' theorem. So you can think about these triangles, these points, these lines as objects. For mathematicians, we care about verbs. So a verb is the function. So you can think of a perspective mapping as mapping one set of points and lines to another set of points and lines with this particular rule that says that corresponding points have to line up with the sun, which you call the center, and corresponding lines have to line up with the axis, this hinge. But there's other functions that take points to points and lines to lines. So we know in linear algebra, you can do this all the time. And in linear algebra, sets of parallel lines go to other sets of parallel lines. But there's other kinds of functions that do this. They're called collineations. So the fundamental theorem of projective geometry says that if you have 4 points and their images, then the entire rest, and you know that points go to points and lines go to lines, then the entire rest of the function is predetermined. We know that. So Desargues' theorem says that that one kind of collineation is these perspective mappings, right? That just like a shadow or mapping from the floor, this tiled floor, onto your canvas through a window. We know from linear algebra, there's these other affine transformations. And so one really cool theorem that I totally love is if you have something that's not a linear algebra one, that's not an affine transformation, then it's automatically a perspective transformation together with an isometry. So you took a photograph and you moved it. That's this notion that every single thing that you do with 4 points going to 4 other points that determines a whole function. So yeah, so anytime you have 4 points connected by 4 lines, even if they look like a bow tie or they look like this Captain Kirk Star Trek logo, it turns out that's actually a weird perspective image of a square moved around somewhere.
Mm-hmm. And you just have to figure out where you should stand to see it as a square.
Yes, exactly.
Are you guaranteed to be able to, I mean, so if it's on the wall, say, is there, do you have to like lift up into a third dimension to be able to see it correctly?
So no, so one of the weird things that happens is if you have a bow tie, we sort of think of like a bow tie as the inside of the bow tie. You would imagine that has to go to the inside of the square. And that is not actually the way it happens. So let's think about something that's much more familiar to us. Can you map a circle through perspective into other weird shapes like an ellipse? Well, sure you can. So imagine that you've got a lampshade, and you've got a circular lampshade, and the shadow that it projects onto the wall is actually a hyperbola, right? We know that. And the light from the inside of the shadow goes to the part of the hyperbola that goes off towards infinity. Well, if you have the bow tie, think about the area like outside of the X as almost a hyperbola. So this is when it would be so wonderful if I could actually draw pictures, but it's a podcast. So on the bow tie, there's 2 sides that are parallel to each other, and then there's this weird X in the middle. The parallel sides extend them out towards infinity from the bow tie, right? That turns out to be like where the square goes. So if you had a square lampshade, it would cast a shadow that would look like this outside of the bow tie. In the same way that a circular lampshade casts a shadow that looks like the outside of the hyperbola, the U shape of the hyperbola.
Okay, my desk lamp is a rectangle, and I'm trying to see if it's
Yeah.
casting the right sort of shadow here. But
some experiments you can do later. I feel like it's this expand your mind on what a square is kind of idea. So
get rid of those old ideas, man.
Yeah, I know that we traveled a little bit from Desargues Theorem, and I want to give you a chance to circle back and
square back
or projectively bow tie back to Desargues Theorem. And I guess what do you love so much about it?
So what do I love so much about Desargues Theorem? So one of the things that I love is that it really tightly connects mathematics informing art and art informing mathematics. So if you ever so Desargues himself, we don't know if he actually wrote this up and published it. We don't have a copy of his original manuscript. We do have something that came out from one of his sort of acolytes, one of his followers, a guy named Bosse. And if you look at so to draw a Desargues diagram, you need 10 points. The 3 on the first triangle, the 3 on the second triangle, the sun, that gives you 7, and then the 3 along the axis. You also need 10 lines, the 3 on the triangle, the 3 on the other triangle, the 3 light rays, that gives you 9, and then the axis. When Bosse first published his diagram was incomprehensible. It had 20 lines and 14 points, and it was just really a mess, and it was hard to even figure out where the heck the triangles were.
Yeah, I don't see them.
Ended up proving this not using sort of standard geometry, using numerical stuff called cross ratios. But the proofs that sort of make the most sense, that are convincing, are proofs that allow us to think about things in 3 dimensions and use art. So that's one of the cool things, is that actually drawing, if you go and you shade in Boss's diagram in a cool artistic way, all of a sudden it sort of pops into 3D and you can see it, but his original diagram, not so much. The same is true of a lot of different proofs. If you try to imagine them as 3-dimensional, if you draw them as 3-dimensional, the proof becomes more obvious. But also, Desargues' theorem is actually useful for artists, because if you want to draw the shadow of something, if you want to draw the shadow of a kite, if you want to draw reflection, shadows and reflections, they are projections, so projective geometry. And how do you know how to draw this? You have to use the fact that the shadow or the reflection or this projective image, however you've made it, is perspective from a point and perspective from a line. So you're constantly using Desargues' theorem to draw these images of images within your image. And yeah, it just becomes so incredibly useful.
So my wife's an artist, but I can't imagine that she would use this, right? I mean, so I mean, if you walked up to a typical artist, are they going to say, "Oh yeah, I use Desargues' theorem all the time," or is this sort of an intuitive thing where people who are very good at drawing in perspective can just kind of naturally draw it that way?
Oh, yeah. So the truth is that Desargues' theorem has really only pretty much been used by mathematicians,
Sure.
and occasionally misused by mathematicians. There's a description in a book by a guy named Dan Pedo of Desargues' theorem to draw the image of a pentagon on the top of a square, and he just completely gets it wrong. And Mark and I think that's hilarious. This book has been reproduced gazillions of times. Anyway, so no, actually artists have this incredible skill. One time we had asked mathematicians and artists at one of our workshops to try to divide the image of a flag into 3 equal pieces prospectively. So imagine you're drawing the Italian flag going back into the distance, right? How do you do this? In the real world, there's the 3 bars are evenly spaced, but in perspective, they're not. And the artist stood up and said, well, you just eyeball it. You just put them here. And I was horrified. This is not a proof. This is not correct. And my colleague, Mark, said, okay, this is good, but for those of us who can't just eyeball it, let's see if we can come up with a construction. And eventually somebody did. They came up with a really cool geometric construction. And Mark had them put this up over the artist's solution, and it was spot on. As a mathematician, I decided to go take an art class, and one of the things we were supposed to do was to draw cans, and so the top of a can is circular, and so the image was going to be like an ellipse, and I could not get the proportions right. Like, my ellipses were so awful. So I would say that Desargues is an incredibly useful tool for drawing things that look very accurate for people who do not know art but who are good at math. That's a really long answer to your question. Yeah, artists don't tend to use it, but it really is a useful thing for drawing things that look correct.
Cool. All right.
And you've incorporated this into a class that you teach to help people. I don't know if the purpose of the class is more math or more like perspective drawing, but it seems like an interesting mix.
Yeah, we have a course called Perspective and Projective Geometry. We actually have a book that's come out that has Desargues' theorem right on the cover up there, and it's aimed at the sort of the intro to proofs level. So it really teaches students to make conjectures about what they're seeing in the world, and then to try to prove those conjectures, but also to try to draw. So it's actually sort of an applied course. So the students, when we introduce them to Desargues theorem, they're actually drawing the shadow of the letter A and then discovering the Desargues theorem and then proving it using many colors and lots of cool lines. So it's so much fun. It's a course that really attracts a very unusual swath of students. They all are students who love math and who are art curious. Almost none of them are good at art, but I tend to get more women than men in the class. I have often had my class being highly diverse in terms of races and ethnicities, and so for me, it's a fun class. I didn't do it just for the sake of promoting diversity in the math major, but it sort of unintentionally has done that, and that's a really good feeling.
Very cool. So another thing we like to do on this podcast is ask our guests to pair their theorem with something. So what pairs well with Desargues theorem? Yeah,
so I think I already hinted at this. So anything that you can eat with chopsticks goes really well with the Sargs theorem, because chopsticks allow you to have wonderful food and do math at the same time, and what could be better?
So basically anything you can eat then, right? You can eat anything with chopsticks, right?
Soup is a little bit tricky, but yes. Yeah.
But you drink the soup, right? That, you know, they give you the chopsticks. You've had ramen, right? There's the chopsticks for the noodles, and then you
exactly. Yes.
Do you have a favorite food to eat with chopsticks?
Oh my goodness. Pretty much everything. I was just realizing ice cream is not so easy with chopsticks.
Yeah.
And I love eating ice cream. I think yesterday was National Ice Cream Day. I don't know. I take my chopsticks with me in my planner bag, and and a spoon. And so when I go to restaurants, if they try to give me plastic things, I use my chopsticks. So basically, yes, anything I can eat with chopsticks, I will eat with chopsticks. And then if I can't, I'll use my spoon.
Nice.
See, we're getting Thai takeout tonight, so this is
very
now I'm really excited. Yeah, right.
Yeah,
I'm coming to your house.
Sure, come on down. Although with all the COVID, I don't think Florida is really a place you want to be coming these days.
Yeah. So I guess this would be a good time to open the floor to questions. So Brian, I was thinking that I would be able to keep an eye on it, and I totally couldn't. So I'm glad that you were keeping an eye on it. So do you have any questions that you'd like, that our listeners would like to ask Annalisa?
I've noticed 3 so far. One is from Joshua Holden. Would Desargues theorem be useful for computer graphics?
That's a really good question. If I knew anything about computer graphics, I would be able to answer that better. I do know that my students who have gone on into computer engineering tell me that the course that I offered on projective geometry was one of their most useful courses. That this idea of ray tracing was super, super helpful. So I don't know if Desargues theorem itself is specifically useful, but the idea of projective geometry is certainly how we understand the world through videos.
We got a request from Doug Burbrower asking for you to hold up the line drawing while I ask the next one. I was wondering, so when we're talking about triangles, we have these vertices that are special points. How does this idea translate when you're talking about, say, like shadows of more complicated objects that might be smooth? You talked a little about circles, but is there anything special that happens when you generalize beyond polygons?
So one of the things that makes triangles really awesome is the same reason why triangular stools are so useful is they're always stable, right? Whereas a four-legged stool can wobble. If you try to draw the perspective image of an object with 4 points, like a kite, it's really easy to make it be perspective from the sun without being perspective from a line. And if you do something like that, it'll look like maybe the kite is planar, but the shadow is curved, which might make sense on the ground. So in some ways it's saying triangles really determine planes. The question of drawing other curves is really interesting because of how you do or don't define curves in projective geometry. So one way you could think of a curve is a collection of points. You could also think of it as a collection of tangent lines. And so I think a way to generalize Desargues' theorem to those would be to be talking about those collections of points and those collections of tangent lines.
And then the third one that got some answers in the chat was, I have a sense that like parallel things, that when they're perspective from a point, that means the point's at infinity when you were talking about projective geometry. Is there geometric intuition about what it means for the line, perspective from a line, for that line to be at infinity? And TJ suggested it was that the objects are translations of each other.
Yeah, so yes. So if the line is that is at infinity, then either you could think of this as being translations, or you could think of it as being a dilation. And so it's a translation if both the axis where the two triangles meet is infinity and the center, that is how you shine from one to another, is also off at infinity. And they're a dilation if the axis is off at infinity, but the center is what we call an ordinary point. So, yes, very cool.
All right. This is new for us, having a Q&A. I mean, it's usually just the three of us, right? You know, me and Evelyn and whoever we're interviewing, but this is fun. I like this interactive.
Yeah, I like that. And people have good questions.
Yeah,
so.
yep.
Great, thanks. Are there any more questions from the chat that we want to get to? Okay, looks like I'm seeing no. So I think this will sort of wrap up the, oh, Brian, yeah.
A new one just appeared. Do cylindrical polar coordinates throw any light on this?
Oh, so I was just about to say to everybody, thank you so much for asking me the questions that I actually know the answers to. And this one, I have no idea. I don't know anything about cylindrical polar coordinates. Sorry. Now I'm going to write that one down and go check it out.
But we can all appreciate the throwing light phrase of the question. Yes. That was very well done. Thank you.
Yep, clever. Yep.
So to wrap up the podcast portion of this, or the episode with Annalisa portion of this, we will have show notes that are available. Our podcast listeners probably know where to find that at Kevin's website. And on that, we'll include a link to your website, a link to the books that you have. Do you want to say the titles of the books that you've written that people might be interested in?
So the first one, the one from 2011, is called Viewpoints, with a subtitle, Mathematical Perspective and Fractal Geometry in Art. And that's suitable for like a first-year seminar in math and art. So students don't need to really know anything at all about mathematics. And then the other one is called Perspective and Projective Geometry, and it came out in 2019.
Yeah.
Okay.
So thank you for joining us, Annalisa, and for doing it in this different, fun format.
I'm really flattered that you invited me to do this. Yeah, it's been so much fun trying to think about how to do this without drawing gazillions of pictures. I appreciate the challenge.
Yeah.
Yeah, thanks so much. Okay,
right.
So there's that part of the episode. All right.
Yeah,
great.
and the three of us can stop our recording. Sorry, that's a little, we probably don't need the the other stuff. But yeah, for everyone else who has joined us, thank you so much. So what we wanted to do with the last portion of the time is to collect, we've called this Flash Favorite Theorems. About a year ago, I think we published an episode of Flash Favorites. I even see at least one person who's joined us is one of the people who gave us a Flash Favorite there, Michelle Manis. So nice to see you. So, and she knows the drill already.
Mm-hmm.
But these are basically 1 to 2 minute snippets from just a lot of different people. And so we'd ask you to tell us your favorite theorem and your pairing for it, because the pairing is a really fun part of the podcast, at least for me. And so I think
I like it too.
Oh, I mean, I was thinking like as a host.
Yeah. Yes.
And I hope guests enjoy them too. I just love how it's built up this like collection of bizarre associations in my mind. I'm like, oh, symplectic geometry, avocados, obviously.
Right.
So you just kind of get all this weird stuff in your brain. So I think how we like to do this is there should be an option for people to raise their hands. I think in the reaction. Oh no, that's not it.
Participants. You open up participants, and then you can raise your hand.
Oh yeah. So if you
click on participants, you won't be able to because you're a co-host. But yeah.
Oh, okay.
Yep.
Yeah, I was wondering. I was going to say, okay, yeah, but if you're a participant, you should be able to raise your hand, and we'll try to basically go in kind of the order that we see raised hands to do this. So hopefully the logistics will work out okay for this. We did have a volunteer. Brian volunteered to give a flash favorite first to kind of kick it off, and then if you raise your hands, and I guess I'll kind of call on you, and I might need to unmute you, and you can share that with us. You're like a very short description of your favorite theorem and a pairing that you think goes well with it.
Yeah. So Brian, you're up.
When Evelyn calls on you, you should be able to unmute yourself now.
Okay.
So one of my favorite theorems is the statement that if the quotient of a group by its center is cyclic, then the group is abelian. And I love at least three things about this theorem. The first one is the proof that I know is like a tour de force of introduction to group theory. It uses elements and representations and cosets and operations in exactly the ways you expect, but it does something a little bit more complex than you're often used to in that context. So I think it makes a great synthesis of that kind of course, so pedagogically. The second thing I love is, as stated, the theorem is useless. If the group mod at center is cyclic, then the group is abelian. But then if it's abelian, that means the whole group is in the center. And so if you knew the center, you'd already know that. And the quotient of the group by the whole thing is trivial. So you'd also already know that. And so it's sort of a weird, useless, I can't think of a situation in which you know that that quotient is cyclic without being able to compute directly that the group is abelian in some other way.
Right.
And then the third thing is that, and so basically if we had longer, I probably want to talk to you about Kurt Gödel's incompleteness and other epistemological kinds of things. This is why I love this one. But the third one is to think a little more geometrically. In some sense, what this theorem is saying is, if you take a group and you sort of contract everything that commutes with everything to a point, you can't be left with something that's one-dimensional. And that makes sense. This theorem is essentially sort of saying it takes two to tango. It takes at least two elements to be non-commutative, non-abelian. And that, if you think about the counterpositive of the theorem, which makes a lot more sense, if a group is not abelian, the quotient by its center is at least two-dimensional. That makes a lot more sense there. And so given the things I like about this, I suggest pairing this with some kittens. And kittens are simultaneously the most powerful and the most useless things in the entire world, and yet they spend all day sort of living in that paradox and not freaking out about it. And so I think that makes them good models and mentors for mathematicians, and they sort of feel like what I like about this theorem.
That is a really good pairing. I like that. That's great.
And I see at least one of our guests has already paired this with I'm not sure if it's a kitten or a full-grown cat, but I see a lovely orange and white cat over there. So excellent.
All right, who's next? Joshua Holden. Can you unmute yourself?
Yeah.
Okay.
So I want to propose for my favorite theorem, Fermat's little theorem, that, and I'm going to state it in the form that for any integer a and any prime p, a to the p is congruent to a mod p.
Okay.
And I'm going to state, why am I going to state it in that way? I'm going to state it in that way because, okay, so actually, let me first say what I like about this theorem is that it's a simple thing that reaches into lots of areas of mathematics. It's in number theory, it's in cryptography, it's an example of Lagrange's theorem in group theory. It's, there's a nice combinatorial proof of it. And the way I phrased it, I think is maybe the most useful way for both cryptography and for that combinatorial proof. So that's why I phrased it that way. And the combinatorial proof that I learned way after I learned the number theory proof or the group theory proof uses necklaces. So that's what I'm going to pair it with.
Okay.
Okay. So necklaces.
Do you have a favorite necklace?
Yeah.
So I was actually trying to think of a food that was like a necklace to sort of go back to the original pairing idea. But other than like popcorn on a string, I didn't feel
Yeah, I mean, calamari is like topologically a necklace, but it's really more of a ring size.
Yeah, yeah. So I learned about these things last week. We went kayaking out at Cedar Key, and then you've seen these little things on the beach. They look like a little blob. You're like, this is a jellyfish, but it isn't. It's called a salp. Has anybody ever heard of these things? SALP. It just looks like a blob. And so we got home and looked them up and found out discovered that's what they were called. And then they form chains in the ocean, and they're called the jelly beans of the sea. I did not put that theory to the test. I don't know. I actually think they're like salty jelly beans. So maybe something like salps.
Maybe. The group chat is saying candy necklaces, which actually would be the perfect thing to prove the theorem with.
Yeah.
Sure. Cool.
And I see Andrew Stacy. If you'd like to unmute and share your flash favorite.
Okay, am I unmuted now?
Yep.
Yes.
Yeah, okay. As an X differential geometer, I'm going to go for the inverse function theorem.
Hardcore.
Which, oh yeah, the amount of my life that I've spent going by the inverse function theorem is innumerable. And it really feels like one of these theorems that shouldn't happen, that you've got a smooth function with loads and loads and loads of derivatives, and all you need to know is that it's injective and the derivative is invertible, and you get an inverse. So it really feels like you get something for free out of that.
Yeah, that is remarkable.
Yeah. So one way of sort of thinking of it is as flows on a manifold, then I think it should be paired with anything that flows, which, given it's quite late in the evening in the UK, probably is a nice glass of wine.
Sure.
Okay.
Excellent. Yeah.
I was thinking of like honey or molasses or something. I guess flowing more slowly.
You could go for a non-alcoholic equivalent if you like.
No. It's almost 5 o'clock on the East Coast, so we're getting close to alcohol time. So.
Oh well, we're sort of sundown here, so.
Yeah. All right, excellent. Thank you, Chad Wiley.
Hey. So my favorite theorem has always been the Cantor diagonalization argument for the uncountability of the reals. And I think the reason that it's my favorite is because it's kind of the first proof that really sort of blew my mind and made me like feel really excited about that. And I think, you can talk a lot about its historical importance and its importance to like the foundations of set theory and all that. But I think it's really great as a way of getting people excited about showing them kind of the real fun of math beyond just like the algebra that they know of from school.
Yeah.
So if I had to pair it with something, I can think of two things. Like if I wanted a specific food to pair it with, the usual proof involves like these lists of sequences of digits, and so that makes me think of like a package of ramen or something. With the noodles laid out. But honestly, I think you could pair it with pretty much any food as long as you paired it with an infinite amount of it.
Sure.
So hopefully it's something you really like.
Right.
Yeah.
So, and I do want to put in a plug if anyone else, if anyone would like to listen to a longer My Favorite Theorem plug for Cantor's diagonalization. That was one of the ones that was chosen by one of our guests, Adriana Salerno. chose that. I don't remember exactly when we published that, but it was probably not all that long ago.
Just last
Maybe
year
last fall.
sometime. Yeah, last fall. And Rebecca Garcia's kind of got at that a little bit. Hers was more about the density of the rationals, but it was still kind of that in that vein too. Yeah.
So yeah,
cool.
You can go back and look at those.
Yep.
I see Paul Rowe, you've got your hand up if you'd like to share your favorite.
Yeah, sure. Everyone can hear me? So my favorite theorem is not really a name. It doesn't really have a name. It's really just the sort of, there's this little puzzle where, a bunch of kids are playing around and they get dirt on their face, and they know they're all going to get in trouble if they get dirty. And so there's this weird puzzle that says, well, how does, no one wants to say who is dirty and who isn't. So everyone has to figure out if they have dirt on their own head. And it turns out that it's impossible for someone to know if they have dirt on their own head. But if someone comes in and says, at least one of you has dirt on your head, then suddenly everyone else can figure out if they have dirt on their head. And so it's this fact that there's this information that is conveyed that everybody knows already, and yet somehow it gets them into being able to learn something new.
And so this is one of the ones where, like, if there was only I guess one person with dirt on their head and they saw that no one else did, they know. And then if no one jumps forward with that conclusion, then everyone else knows there's at least two. Is
exactly.
It one of these kind? Okay.
Exactly, right. So like the one case where you actually would learn something new is if you were the one person with dirt on your head. And so that gets that inductive argument started.
Mm-hmm.
Cool.
And as far as pairing, gosh, I don't know. Something redundant, belt and suspenders or something.
I was saying something that would get you dirty, like Cheetos, or
oh, that's good.
I mean, it probably wouldn't get on your head. Hopefully, I guess if you had an itch, we're not supposed to touch our faces, but
no, I like that.
yeah,
spinach on your teeth.
Oh yeah.
Okay. Right. Okay. Excellent. All right. Thanks for that, Dan McQuillan.
Hi. So my favorite theorem this week anyway, an odd prime is the sum of two squares if and only if the prime is congruent to 1 mod 4. This is an amazing theorem. One direction is almost trivial. If you just kind of imagine what a square could be mod 4, you get one direction. The other direction is really, really tricky. It seems natural, and there's lots of different proofs, and they're all really sophisticated and complicated. And it's just wonderful. Many of the proofs are just absolutely wonderful. So that's one of my absolutely favorite theorems. And I'm going to pair it with pesto because it has many ingredients, and it seems natural, and it stays with me for a long time. So
and when it's done right, it's very good. Yeah. Yeah. All right. Anybody else? It's the pairing. Nobody wants to give the pairing. That's always what it is.
Oh, TJ?
Yeah, I don't have a raise hand button anymore.
Okay. Oh, you're a host. That's
right, because I'm a host. Yeah. So I've been thinking about this, and I keep going back and forth between two things. But in the end, I think I have to stick with my heart. The first bit of math that made me super, super excited was learning the theory of covering spaces. And so the existence of a universal cover is the thing that I like. That's my favorite theorem. And I'm going to pair it with a stack of pancakes.
Sure.
All right.
Deck transformations. That's
we make pancakes every Sunday morning as a family in my house, and so this is that's a special thing.
So I make pancakes every Sunday, but my wife and son are in bed while I'm doing it. So how do you get them out of bed to help you make the pancakes?
My middleest child and I have a tradition of making the pancakes. It was his idea to do originally, and so we started this, and it eventually we've conscripted other family members to make things to go with the pancakes, and so now we all get up and make breakfast together.
Oh, that's nice.
Yeah, it is.
I need to train my family to do that.
I see Lauren, you've got your hand up. If you'd like to unmute and share.
I've been encouraged. I don't usually think of myself as a theorem type, which is why I say that, but one of my favorites is the one that says that the product of the eigenvalues of a matrix is equal to the determinant of the matrix.
Mm-hmm.
And I'm a fan of that one for a mix of reasons. One is just the sort of gentle rearrangement of terms that you get to do in the characteristic polynomial to show it. And the second reason is because of all of the things that it lets you do with stability in dynamical systems and looking at bifurcations and such based on where the determinant has a particular sign and all of those related things. And the third reason is a little bit selfish, which is that I put it to wonderful use in one of my qualifying exam questions. Goodness, however many years ago that was now. And I think I'm going to pair it with pasta.
Okay.
Because of the different shapes that it can take and how you can either align things in a particular way to make lasagna, or you can just mix it all together and get useful stuff out of it anyways.
Nice. Excellent. Very cool.
Yeah.
All right. Anybody else want to give it a shot?
Tian?
Joanna Franklin?
Oh, okay.
Sorry.
Yeah. So I'm a research logician, but a lot of people have already said things about cardinalities and whatnot, so I'll go with my teaching interest, which is probability.
Okay.
And I've got to say Bayes' theorem, just because it is so cool for everything. Like, this is the thing I tell my students. Someday you're going to be sitting in a doctor's office, getting a test result back, and you will want this theorem on that day, I promise you. And you will remember what I'm telling you, and as a result, you will not panic.
Yep.
So honestly, I would have raised my hand sooner if I had everything ready to go. But I think I'm going to have to do some sort of thing like a cupcake with some sort of filling, because you might know the general kind of fillings that go with the cupcakes. But if you know the flavor of the cupcake, then you have to guess the filling. That's the only kind of pairing I can think of here.
Sure.
If anyone has something better, I'd love to know.
Yeah, the prior is important when you're trying to decide if you want to eat that cupcake or not.
Oh, no, it's a box of candies. Those Valentine's boxes of candies.
Oh, yeah.
Where you just have to guess whether it's coconut or raspberry or what it is. That's exactly it. Thank you. This is perfect.
Yeah. That assumes that there's a kind of cupcake or chocolate that you don't like, which is not my life. So
I don't know. Some of those chocolates, like in a Whitman sampler, are kind of gross. Like there's one. I don't know which one it is, but you bite into it.
Well, I'll take that one.
Okay.
For you.
All right.
Annalisa will too. Yeah. So Tian, you raised your hand earlier. Your actual hand, since as a host you can't raise your virtual hand.
All right. So my favorite theorem has got to be the Noether isomorphism theorem, or the first isomorphism theorem, at least the group theory version that I learned as an undergraduate. And for me, it's sort of a personal thing. At the time, I had already dropped out of school at one point, and I worked for a while, and I returned to school, and I was really only a math major because those were the classes I had passed. My first dance round, so my quickest path to like an undergraduate degree. Like I had no idea what I wanted to do with my life afterwards. But we had studied normal subgroups in its chapter, and we had studied group homomorphisms in its chapter, and they kind of seemed sort of disjointed at the time. And when we studied the first isomorphism theorem, it showed like this deep connection, right, between like the normal subgroups. The study of those were the same as the study of group homomorphisms, essentially. And I was like, oh my God, there's this beautiful connection between these two things that had seemed disjointed before. And of course, pedagogically, it's designed that way in retrospect, right? But at the time, now I realized that I was like, this is such a cool thing. And it's so great that there's this thing that connects different pieces of math that I've known about that I wanted to do more of that. And so that and other experiences I was having at that time was what led me to figure out what I actually wanted to do with my math degree, to go on to graduate school and to do all the things that happened subsequently. And so, and also what made me want to be a teaching faculty later on in life. And I think around that time is when I made that choice. And that theorem's always associated with that time in my life. And so I have this personal feeling about the first isomorphism theorem. And so what would I pair it with? I guess I would pair it with spam musubis, because I was in Hawaii doing my undergraduate at the time, and I was eating a lot of that. So yeah, those are things that that resonate with that time. So, yeah.
I'm sorry, my audio cut out for just a moment while you actually said your pairing. What was it?
Spam musubis.
Musubi.
Right, yeah.
It's a sandwich, right? With the,
I only heard bees, and I was like, I'm pretty sure he wasn't eating bees. So.
He might have been eating bees. It's actually, I just learned about musubis because there's this show on Netflix now. It's called Crazy Delicious. I don't know if anybody has seen this, but it's really strange. But anyway, they have to make these sort of interesting things. And this one woman made, like, they had to deconstruct the sandwich or whatever. And she made musubis and had spam, and it looked delicious to me. So.
Very nice.
All right, well, I think it's, in the interest of time, it's time to wrap up. But thanks everyone for being so willing and participating in our Flash favorite theorems.
Yeah.
Excellent. So 3 little things. One, I would like to publicly welcome TNG to the leadership of Talk Math with Your Friends, the person who just shared last. Stephen Klontz has retired. He's still a good friend of Talk Math with Your Friends, but Tian was very interested in being part of the group, and so he's now part of the leadership group. And we're definitely interested in continuing to have other new voices. So if you're watching this or live or on YouTube, we'd love to know if you're interested in being involved in the leadership. The second one is a very brief announcement of next week. So next week's talk is by Noelle Sawyer. She's going to be talking about the situation with specification. So I'll just leave that up as we do this. And then the final one is, will you please join me? You may maybe unmute your microphones. Please join me in thanking Annalisa, Evelyn, and Kevin for this session.
Yay! Everybody.
Thanks for having us.
Yeah, thanks for having us. This was a really fun idea. I'm glad we were able to make this happen.
Excellent. Thank you so much, everybody. I hope to see you soon.
Okay.